Ugh. Hi, Casey. It's working.
Hi.
Why is this not working?
Wrong with it?
I have no clue. There it is. I had a light somewhere. Where did it go? Oh, I was so organized now. I'm so not organized. There we go. There it is. It was hiding under the box.
It's okay.
There we go. It's a very bright light. How are you?
I'm good. How are you?
I'm fine. I've had a bit of a headache today, so I'm a bit.
Oh,
My
are you
mind
okay?
is feeling a bit slow, but we're getting there. It is nearly the end of the day, which is good.
Yeah.
How's physics?
Um, it's not too bad.
Cool. How's electricity going?
Oh, ow. Better.
Good. What were you doing this week?
Today we just done a past paper,
Okay.
but we
Which
done it
one?
under like timed conditions, but not the full thing. It was like just to see if we could keep on track with the time, so we could still like talk and stuff.
Okay.
But told us to do like 15 multiple choice questions in 18 minutes, and I done 9.
Okay.
I'm not sure how the time conditions work, but I get extra time anyways.
Good. Ah, Dean
But
is
I got 6 out of 9,
okay.
which isn't too bad because I didn't know how to do one of the questions, and the other two I messed up because I rearranged wrong.
Okay. There's all things to work on. I
Yeah,
was thinking we could look at which past paper did you look at?
it was like 2019.
Oh, that's fine. I was thinking we could look at I think one week lately we looked at 2022, but we looked at paper two. I thought we
Okay.
could go back and look at paper one because there's
Mhm.
lots of electricity questions in there.
Yeah,
Let me bring it up.
rearranging the equations is something I'm not very good at though.
Okay. Let
Especially like the length and time dilation ones.
Yes, those are.
Because it's like a square root and it's squared. That's one of the questions I messed up earlier because I rearranged it wrong. Because you had to find like the velocity.
Hmm.
So it's a
And it's
bit,
in the square root, but
yeah. My teacher showed me how to do it, but I was a bit lost when I was doing it the
okay.
first time.
We'll come back. Let's do some electricity, and we'll come back to that later. I'm actually trying to. I was actually for last night. I was doing some marking and stuff, and the rearranging of formulas seems to be something a lot of people just find quite challenging. So I was going to see if I could find some other resources to demystify it a bit. So I'll see what I come up with. Um, that makes it clearer how to the different steps to take. So that's something that's on my kind of list of things I want to research just to see if I can better understand the way where the kind of key bits that people trip up on rearranging and how to signpost away from those trip up places, if that
Yeah.
makes sense. Have you done this bit in university? And
Yeah.
yeah, let's do this one then. So we've got this oscilloscope just shown. I'm going to move that away so you've got the numbers down here. So the Y gain is 2 volts per division, and the time base setting is 5 milliseconds per division. And which row is correct?
For the peak, does the Y gain setting have anything to do with it?
For the for
When
the
you're finding the RMS, because you use the peak over root 2,
Yes, it is. So the Y gain, each of these
is 2.
is 2. So you're going to have to think, what is the
3
peak?
times 2.
Why is this not working?
You do 3 times 2.
Let me a second. Let's use this one. One, two, three. Yes.
Okay.
This
I
work.
was double checking. I've only ever done them with like the Y gain setting being 1.
Ah. That in properly.
I need to find my calculator.
Yeah, you do that. I'm just get my whiteboard to work because it's not. It's just flashing. And some naughty person been in here and fiddled with it. Very good. Oh, oh, there it is. Oh, that's good. Why is it not writing?
Um, I got B.
That's correct.
I was gonna say that looks like a really big number for frequency, because normally it's like really small numbers.
It depends on the type of wave you're dealing with. So you
Yeah.
think about the with the way that frequency velocity of a wave is the frequency times the wavelength. And if you think about with just electromagnetic waves, the wavelength varies from being really long, like round about meters, to nanometers, which is tiny. So the frequency again can vary hugely depending on the type of wave. And sound waves can have quite um
It was not like gamma rays that was the smallest in that
gamma
fact.
rays. Gamma rays are, I think they're like 10 to the, I think it's the minus 12 if I remember correctly.
I swear the like longest one was either radio waves or microwaves. I think it was
It's radio waves.
radio.
Radio waves, and there's a huge variation. Um, there's a huge spread in the electromagnetic spectrum for radio waves. Let me get rid of that wee drawing. There we go. So yeah, frequency can, just like wavelength can take a massive range of values, so can frequency.
Yeah.
So we've got three resistors connected to a 3-volt power supply as shown. The power supply has a negligible internal resistance. The power dissipated in the current is.
How do I do this one?
So first you'll need, so the equation for power is V squared over R. I'll just double check I put it the right way around. Um, So you're going to need to find you're basically, first of all, you're going to need to find the resistance.
Okay. So I have to find the ones in parallel and just add the one in series.
Yes.
Okay.
Yes. There's so many variations of the power equation.
Yeah. 0.97.
Let me just the
That's not even an option.
where's the one over button?
Mhm. My answer's not even an option, so
Okay, so let's first find the resistance. So the resistance here is 1/6 plus.
oh, wait, I know where I went wrong. The writing was really small and I thought the 6 was a 9.
So the nine is a 9 up here.
Yeah.
The top one's 9, but these two are both 6.
Okay, wait, let me just. I was thinking that looks really wrong.
It comes out to be a nice number.
Yeah, normally
There's
it's quite nice numbers. Oh, wrong side.
me. Um, oh, there it is there. Delete, delete, delete.
Um, yeah, my answer's still not on there.
So the resistance, these two added together gives us a resistance of 1/3. So the resistance here is 3 ohms. So 3 add 9 is going to give us 12 ohms. And our voltage is just 3 volts. So it'll be 3 squared is 9/12, which gives us 0.75.
I forgot that when you're doing it, you have to do like, well, we got told to put it in brackets and do it to the power of -1,
Ah,
but I forgot to do that.
okay.
I always forget to do that. So I got 0.3 instead of the 3.
Yeah, it's an easy mistake. So at least if you did that, you did this here, and you look here and you got none of the things here, you can go back and think, well, what did I do wrong?
Yeah,
Um, then you know there's something's gone wrong with the calculation, so you can go and check.
because I will have extra time, so it'll give me time to go and look over my answers again, because I didn't
It
get that in
will.
that 5.
How long do you get for your extra time?
25% extra. I got it for all my classes.
Brilliant.
I didn't
That's
even
good.
ask for it in any of them.
Wonderful. Oh, I'm really glad.
Yeah.
That's good. I'll just take that pressure off.
Yeah, it means I can like take my time a little bit more rather than trying to do what I done last year and rush through the paper and still not even finish it.
Good. Another resistor one.
Oh, this
So
one's long.
this one is quite long. 6 resistors, each has a resistance of 5 ohms. They're connected to a 12-volt power supply. The power supply is negligible in terms of resistance. Which row on the table shows you the total resistance and the potential difference across X and Y?
Can I just combine the resistors at the top and the resistors at the bottom? Or do I have to them?
So yeah,
Because,
so because these are in series up
yeah, so I
here,
can just combine them.
yes.
Okay.
So it's like you would treat it as if it were a circuit like this. This is your 5 ohm one here. And this would be like
Total circuit resistance. Either one or two.
and that keeps on going. So it's like saying you just combine these, so it'd be like 12 ohm, 10 ohms and 10 ohms. It's like having, and then those two are in parallel. So you have to deal with these two, the 10 and the 10 in parallel to get the total resistance of this part of the circuit.
Okay. How do you find potential difference again?
It's just the voltage.
Just the
So,
voltage.
so once we get this, um, so once we get this, so if you combine these, then you get, I'll just draw that little one here, and then it goes here, and that's 5 ohms. So it's like then combining, so it'll be like having, so this is 5 ohms, this one's 5 ohms, and the total resistance of this middle part of our circuit will be a resistance here. So we can treat that almost like its own little resistor. And this is X, and this is Y.
I got 5 ohms for the middle one.
It's 5 ohms.
Just in case that makes it easier so you know the answer.
And the voltage is 12. And so if the voltage is 12 volts, and we know we've now got basically three resistors, all with a resistance of 5 ohms, we can then think, well, how does the voltage behave in series?
Is this like when you can do the ratios?
Yes.
Okay.
It's Becca. Mhm. Go and tell Becca to come and get Matt. Or Matt, Thomas, you can take Matthew. You're a big boy. Go to Tom. Matthew boy, come around here. I'll pass it over to you. Go to Thomas. Yeah, fine.
Um. Oh wait. B.
Yes, it's three. It's B. So we've got our
60
total
minutes of
in the
voltage.
circuit is 5 at 5 at 5, and 12 divided by 3 is 4. So 3.
I'm too tired for this. I started trying to split 100 into three, and I was like, wait, that doesn't make sense. The answer's going to be two or four.
Right. One of
Mm.
our EMF problems. Um, the resistance of the variable resistor is set to 6 ohms. What is the lost volts due to the internal resistance of the battery?
Mm. What would be like the thing you use for lost volts?
So let's
Like
first.
a symbol.
So we'll come to that in a wee minute. We need the current first. How do you find the current in the circuit?
Um, V equals IR.
So it's V equals IR, but we're going to use the EMF. There it is equal to the current times the total resistance in the circuit. So if we could think of the internal resistance is added is in series to this variable resistor, we can add the resistances together to give us the total resistance, and then we're able to find the EMF, which will be the same as the 12 volts in this cell here.
Yeah. I was writing down the things for it. I was
Oh,
writing down the because our teachers said to use river to remember it.
oh yeah. So it's 10 volts, 10 ohms even.
Would V be the lost volt?
No, so this is where we need to be careful. So our EMF is here, is the 12. Our V, this is over the potential difference, so that is like here. So that would be our V potential difference, and that would be the same as what would be measured over here, because it's the same. It's just like you're measuring it here, but it's also going to come here too, because it's just there's nothing else in this circuit. So that'd be our V. If we did that, that's our V potential difference. Now, remember we said we could think of this as like we're pushing the current out of the battery into the circuit, and the lost volts are the volts that are used in the pushing of the current out of the battery. And so once we pass this little box, those volts are lost. But they have to add together to give the
Um,
so it's going to be.
so you find V,
So
but
no, you don't even need to
I'll
find
find
V.
E.
The potential difference will the lost volts will be the current times the internal resistance.
Oh, I don't remember this. I know I learned it. I
You
just
could
don't remember any of it.
it's it is one of the trickier parts of the electricity stuff. Or you could find the potential difference volt. So we could say so the V here would be equal to the current, which we've just worked out as 1.2 times 6. What's that? 1.2 times 6 is 7.2. And then we can subtract it from the 12. So 12 take away 7.2 would give us 2.8, which is not one of the answers. What have I done? 12 minus 7.2. That's better. 4.8. What's the push their own number? 4.8 volts would be the lost volts. And if we do 1.2 times 4, it comes out as the same. So you can either do it by finding this would be the lost volts, or you can find what would be the potential difference over the resistor, which is the current times the 6 ohms, and then subtract it from the EMF up here, and it comes out as the same.
Okay. So I can either find I with IR. Wait, would I do E take away IR?
Um, no. So this R, little r, is here. So if you
Yeah.
do, so E take away IR is going to give you the 7.2. The
Yeah.
IR is this here is the lost volts, because this is the current as it passes through the internal resistance.
Okay.
So it's the voltage over. here. The other way to think of it is, remember we were talking about, as we just draw a circuit. Just do just random little cell here. And if we have resistance 1 and we have resistance 2, we know the total resistance. The total resistance in a series current circuit is equal to R1 plus R2. When we're looking at this, our little EMF circuit here, we've got the internal resistance. It's in series to this variable resistor. So just what we said here, the total resistance is the same. But in the same way, when you've got the total voltage, and I'm just going to get rid of this down here because it's isn't going to be in the way. If we put a voltmeter here, let me make that bigger.
It's like a light bulb.
It's like a light bulb. V1, and if we put another voltmeter here, V2, V1 plus V2 in series is the voltage, the source voltage. Actually, we'll call it Vs actually instead of Vt. The voltage of the source is equal to the two voltages added together, and how the voltage is shared between the resistors is through the current, which is the same everywhere, times R1, and the current times R2. These will give you the voltages here and here. But this whole setup with the internal resistance is pretty much the same sort of circuit. You've got two resistors in series. The current is the same everywhere because they're in series, but there is the voltage over this here. This will be the lost volts. Over this internal resistor. This is your lost volts over here, and this is your voltage, the potential difference voltage that you would measure at any place in this circuit was over this resistor. Does that make sense?
Yeah.
So that's a way to think about our EMF circuit that is more in keeping with what you've done before with this kind of very simple two resistors in series, simple little power source. But instead of the resistor 1 and 2 being out here in the circuit, this resistor is actually inside the power source. But it behaves in exactly the same way as if it was out here.
Okay. That makes sense.
And so the voltage lost is the internal one here. And it makes it more complicated because it's sitting right beside the power supply voltage, which is this is your EMF. Let's clear this. I think we might have another EMF one.
I don't like EMF.
I don't like EMFs either. Oh no, it's not. It's capacitors. Have you done capacitors yet?
No.
We can leave the capacitor. This is also a capacitor. And then there we are finished the multiple choice on this paper. Shall we look at another paper, or shall we look at any specific? Shall we look at the rearranging of the
Unseen formula. Or a rearranging of just equations.
I was thinking about the special relativity one. Hi.
Bye, Emma.
Bye.
Bye. Love you.
Bye.
Yes, Bob.
See you after.
Is that your dad?
Yeah. Going to training.
Cool. Noah's not back. Noah goes to the gym after his work, so yeah, he leaves like half six and he gets home about 8.
Ooh.
Yeah, full long day. He's 18, so he's got the energy to do that. Anyway, digressing. We could rearrange special relativity one,
Mhm.
or we could. Is there an unseen formula one?
Um, there's got to be one. Unseen formulas are really difficult
Is
to like
that,
rearrange.
do they have that in maths, or is that they wouldn't have that in a physics paper? I've not seen anything like that. I can't think.
Unseen formula?
Yeah, in physics.
Yeah, they do.
Oh,
Yeah, they give you a formula and they just give you the numbers and you have to find the value.
okay. Let's see if we can find one in a past paper. Let me.
I
If,
done one of them earlier.
let me just bring that one back up because we'll have a wee look and see if there's one in there. Um.
If not, I think there's one in 2019.
Okay.
Could be earlier in the paper.
Okay, this will be the one. Astronomers use the following relationship to estimate.
Oh, yeah.
Here it is. To estimate the mass m of a galaxy, where v is the orbital speed of the star in the outer regions of the galaxy, r is the orbital radius of the star, and g is the gravitational constant of the universal constant of gravitation. I was renaming it there. Star orbits at a radius of 4 times 10 to the 20 meters in the outer regions of the Triangulum galaxy. The orbital speed of the star is 120 kilometers per second. Based on information, what is the mass? Well, this is not a rearranging one, but it is a one to be careful with.
Because it says kilometers per second it wants the velocity. Wait, no. Yeah, it wants it in meters per second.
Yes.
So you'd have to times it by 1,000, or you could write like 10 times 10 to the power of 3.
Yes, you could.
I swap between it.
Yeah.
That's what one I remember. Do you want
Um,
to do it?
yeah,
Or
do
do you
that
want to
one.
try and rearrange it?
Let's rearrange it. Let's make um V the subject.
V. Oh.
V.
Square root of mg over r.
Let's see. So the G comes up here. V squared R. Then we've got V squared M G over R, and then the square root of M G over R.
I actually got it right.
Great. Let's see what else we can find. Let me just delete that. I'll go to the beginning because it might. I kind of just skip right through all the other stuff because we were looking for electricity.
Do you want me to tell you when the prelim is? Or do you
Yeah,
already know?
I keep forgetting.
Um, Physics prelim is the 4th of December.
Okay,
Math prelim's the 1st.
right, so right at the beginning.
Yeah.
That's 3 weeks away, isn't it?
Yeah.
Wow. Why is it nearly December?
Component weight is so fun. I don't like tension.
Yeah, I don't like I don't never liked tension either. Yes.
Component weight is easy because you just have to remember the formula. But did they ever actually ask you about mg cos theta?
No.
Because I was going to say I've not seen anything on it, so is it just mg sine theta?
Yeah.
Because we were told about it, but it said like acting into the slope. Well, not into the slope, like perpendicular rather than parallel.
That would come into play. I think it'd probably come into play in advanced physics. I think.
I think I'm just going to stick with higher. I'm not going to lie. If I can get my grade in higher, I'm just gonna leave it at that because if I mess up, I swear if you do like advanced higher, they don't really look at your higher.
Um, if you were doing, I think it probably depend. So if you were in six, so in sixth year, if you were applying to UCAS on your grade, you'd have your higher grades. You're applying to university. They're going to give you a place. If you've got the grades of the higher, they would give you a place even if before you got your advanced higher places, your advanced higher grades.
Mhm.
Um, what's this one? Oh, electric field one, magnetic field one.
Oh, we haven't done that.
Okay,
We haven't done any of Unit 2.
right.
We've done Unit 1 and most of Unit 3. I think we only skipped capacitors because he said that my teacher said it wasn't going to be on the prelim. And he was like, do you
Okay.
guys still want me to teach it or do you want to wait till after the prelim? And everyone was like, no, wait till after the prelim. We don't want to learn it now.
Yeah.
So we're just getting revision.
So you've done everything that you're going to get in the prelim. Okay,
Yeah.
there's none in here. Let's, let me grab, um, another paper.
For a
Um,
lot of my classes, we're just doing revision now. Like most of the prelim work's done. I think we're done with math as well.
okay.
Maybe. I'm not sure. We're either done or really close.
You did a wee bit integration, did you say that? Was that what you said on?
Yeah, we've done integration, but we've done like kind of simple ones.
Okay.
Like you didn't have to integrate really long things.
Let's do 2018.
Anyways, we can do either topics now because I kind of have to revise both of them anyway.
Yeah. I'll just see if I find out rearranging one quickly. Are they usually paper one or paper two?
Um, I don't think I've seen it on paper too.
Yeah, it sounds like a paper one type thing.
I feel like it would be paper one because putting it on paper two, you've got nothing to kind of reference your answer to.
Here is
But
this
that one
is
looks pretty bad.
essence of the uncertainty. So a student carries an experiment of specific heat capacity of a solid with the relationship C equals E over M, change in temperature, delta T. The measurements of percentage uncertain, um, the measurements of the percentage uncertainties are shown. A good estimate of the percentage uncertainty of the value of C is.
Value of C.
Yeah, so C is your specific heat capacity. And if you're going to put in,
Or you want me to solve it or rearrange it?
so you don't need to solve it. So so what would be the percentage uncertain, if you use these
Oh.
measurements, what would be the percentage uncertainty?
Do you have to estimate it or can you calculate it?
You don't need to calculate it. So if they've measured the energy supply to as 5,000 joules with a uncertainty of 1%. The mass of the solid has been measured as 0.2 kilograms with an uncertainty of 2%, and the change of temperature has been measured at 4.5 degrees with an uncertainty of 5%. What would be the uncertainty of your measurement for this? If you're using these to plug into the formula, what would be the uncertainty in your specific heat capacity?
Like 3%? Wait,
It's
no, 5%.
the
Wait.
five.
Wait, I misread it. I can wait. I didn't see the percent symbol. I thought it was like you know
Oh,
how
plus or minus degrees.
yeah.
Ah, yeah. No, so yeah, it's just a 5%. So you just pick the biggest one.
Oh.
Um, And that's a self-finished it. Okay, shall we just do some things in this paper then? So we can't find.
Sure.
Let's do that.
I'm too tired
Electricity
for this.
or dynamic universe or
I'll
anything.
start with dynamic universe because I haven't done very much of it recently.
Yeah. So a car is moving at a speed of 2 meters per second and now accelerates at 4 meters per second until it reaches a speed of 14 meters per second. The distance traveled by the car during the acceleration is.
See?
Let me just write them. We don't need T. We've got A. The distance is what we want. That's what we want. Our acceleration is 4. Our initial speed is 2. And our final speed is 14. So the equation we will use is I'll use v squared equals u squared plus 2as. So our v is 14 squared, 2 squared plus 2 times 4 times s. Where is my calculator? So we'll have 14 squared minus 4. That equals 192 equals that's meant to be an s. 8s. So s is going to be divide that by 8. 24. So did you say C?
Yeah,
Brilliant.
I rearranged it right. It
Yes.
normally happen.
So a ball, what time are we at? Oh, fine. A ball is dropped from rest. Ball is dropped from rest and allowed to bounce several times, as shown as the velocity of the ball varies with time. The student makes the following statements about the ball. So, let's put that here so we see it all. The ball hits the ground at P. The ball moves upwards between Q and R. The ball is upwards between R and S.
I put that 1 and 2 were true.
Right, let's see. So he drops the ball, so it hits, goes, speeds up, speeds up, speeds up, speeds up, speeds up. And then
Is that not the impact time when it hits the ground?
P is going to be when it hits the ground, and then it bounces back, and the velocity will start to drop. And at 0, it's at its highest point, and then it starts to fall again, and gaining weight in the opposite direction, speed in the opposite direction, so it hits the ground. Wait a minute. So it drops the ball, bounces, and it's going up. At 0, it's going to be velocity 0 is at the top, and then then it'll.
I thought Q was just the impact time.
Q is the impact time. You're right. Q is that P is up here. It kind of stops, but then it goes in the opposite direction. So that's it. Bounce backs. Yeah, that's its bounce back. So it's bouncing up. So it's going up. It's slowing down. There's when it comes back. It bounces and comes 0, and then it's come back down. That says the velocity is 0. It's up the top. It must be at the top, but then it doesn't change. Yeah, the velocity then changes into positive, and then that's going to be the impact time as well. So the ball hits the ground at P is correct. That's the impact. The ball is moving upwards between R and S. Q and S. Q and R even. That is correct. The moving is moving upwards between R. That won't be correct because it's going to be, if it's 0, that means it's bounced up and it's going to come back down. So it's going to be. Do you say 1 and 2 are correct?
Yeah, I put D.
Yeah, D's correct. So a block of mass 6 and a block of mass 8 are connected by a string. A force of 32 newtons is applied to the blocks as shown. A frictional force of 4 newtons acts on each block. The acceleration of the 6 kilometer 6 kilogram box is.
$1.7.
1.7. So we've got the F equals A. So the force that the resultant force is going to be 32 minus 8. So force is going to be 24 newtons. So 24, and we're talking about the 6 kilometer.
I done it for the whole thing because the
Actually,
acceleration would be the
it's
same.
going to be the same. It's going to be the same for the full thing because you're going to have.
It's got to drag the 8 kilogram block as well.
Yeah, because if one's accelerating quicker, the force is going to be acting on both of them. So you're going to have 6 plus 8 times acceleration. So 8 is going to be 24 over 14. Yep. 1.7. Yep. Meters per second.
Yeah, I'm actually getting it now a bit more.
Let's clear these drawings.
I swear my unit tests are harder than the past papers I'm doing.
That's sometimes good though, because if they're harder, it's forcing you to think more deeply than the past paper than your if they're a bit harder. That should
Yeah, but
apply.
then I'm doing the past papers and I'm only struggling on a couple of questions, and then I'm doing the unit tests and I'm getting like 50%.
This is that look at it as a positive.
Uh-huh.
Um, person stands on a weighing machine in a lift. Let me draw a wee lift here.
Descends and the speed increases downwards, so the
The lift is at
reading
rest.
on the weight machine's gonna continually decrease.
This lift now descends. So there's a force, so it's going to force down, and its speed increases at a constant rate. So it will be higher. It'll be a constant value higher than, it'll be A.
Hmm?
The value will be a constant value higher than 700 newtons on the scale.
I thought it would go lower. Because we done this in the lift where we
Oh,
had
yeah,
a
yeah, yeah, yeah.
scale.
No, you're right. You're right. It's going down, not up. Yeah, it's going to be lower. Yeah, sorry.
I just remember being told that you feel like lighter when you're going down and you feel heavier
You
when you're
do. I was visualizing the wrong.
It's okay.
Yeah.
So would you
Oh,
write its constant value lower than 700 or continually decrease? No, no, it won't
it'll be
continually
constantly.
decrease.
It'll be a constant value. If it was continually decreasing, the acceleration would be constantly increasing. It'd be getting faster and faster and faster. If you've got no.
Because I would have said D, because it says it's
Oh,
increasing.
yes, it is increasing, so there's a constant acceleration. It's not just an initial. Yeah, you're right, it's constantly decreasing because yeah, as long as there's an acceleration force, it's going to be decreasing until the acceleration stops because you've got this constant unbalanced force on acting on him. Yeah.
Okay. Wait, so what would be the answer?
D.
Okay.
Um, Um, Enceladus is a moon of Saturn. The mass of Enceladus is 1.08 times 10 to the 20 kilograms. The mass of Saturn is 5.68 times 10 to the 26 kilograms. The gravitational force of attraction. Oh, here's a rearranging one. The gravitational force of attraction between Enceladus and Saturn is 7.24 times 10 to the 19 newtons. The orbital radius of Enceladus around Saturn is what?
My whiteboard doesn't fit the whole thing.
Let me just remind myself of G. It's 6.67
6.67 times 10 to the minus 11. Which
minus.
one I put it locked in my head and I don't know why.
Yeah, it used to be locked in my head. It's fallen out over the years. I remember the 6 I couldn't remember the times 10 if it was minus 12 or minus 11. Um,
So I'm gonna have to double check it when I do my exam. That would be really embarrassing if I messed it up.
yeah, I think I always just double checked it when I was doing the exams. I was just quickly, even though it was kind of so imprinted on my brain, I would always just double check it because you just didn't want to. That would be just Yeah, you're right. It's embarrassing.
Um, would I be able to just multiply by r squared and divide by the force?
Yeah, so we just write the big mass times little mass over r squared. So so you can absolutely, so r squared will be over here. Then you'll have your 6.67 times 10. Actually, I'm just going to rub out the top up here.
I'm just double checking before I actually rearrange because
Times 10 to the 11 times the mass, 1.08 times 10 to the 20 times 5.68 times 10 to 26, and then divide it all by the force. 7.24 times 10 to the 19. So yeah, so the r squared is on the bottom. So if you multiply the left-hand side by r squared and then divide through by the force. And then remember to take the square root at
yeah.
the end. Because I've no doubt one of the wrong answers is the radius squared.
2.38 times 10 to the power of 8.
Let me see. There we go. And then
Oh, so A. I thought we were doing multiple choice.
I don't know how to get my answers on this.
Do you have any
Oh,
calculator?
I've got this calculator and I've
Oh,
just,
that's one Sophie has.
I don't know how to recall. Oh, there it is there.
Hmm?
How have I missed that?
To be fair, I don't like using Sophie's. I had to use it one time and I was lost. I'm used to my one. Do they still sell it?
This one.
The one that I have?
Let me see. I don't think they do.
Because I like my one, so I'm trying to keep it because I don't want to get that one because I don't know how to use it.
Oh, this is a horrible one. I've messed up with I've messed up somewhere. Um, Let me just try again. Let me try. Let's do it that way. Yeah, no, this is like there's videos of people doing this calculator when it first came out a couple of years ago, and the chaos it caused in classrooms because it just people like teachers teaching the way of lots of simple little things that you just do intuitively, and it didn't do them right, and it just was awful.
Yeah. It's really hard to find the buttons because they're in such weird places.
They are, but it doesn't do. If you're doing if you do a division and you've got numbers in the standard index form, it doesn't read them as standard index form. It reads them as if it reads them actually pretty well. It applies the rules of Bidmus really pedantically. Like, say if you were to do like 3 times, I was just 3 times 10 to the power of 8 divided by 4 times 10 to the 2. And you were to put this in this calculator just like that, it wouldn't give you the right answer because it would read it as so Bidimus would do division first. So you did if you it would divide 10 to the power of 8 divided by 4, and then it would multiply the other two parts of it. So you
Oh.
have to either put it in brackets.
Wait, what did you get when you put it just in your calculator?
This one.
Yeah.
I got something that wasn't even on there, so I've done something really strange. That looks
I
pretty
got
fair. It was like to the power of 50 something.
I got
What?
750,000.
1, 2, 3, 4, 5, 6, 7, 8. Did you say A?
Yeah.
Yeah, that's the one I got the second time I did it. Um, yeah, so if you on this calculator, you either put in brackets or you would do this sum by using the fraction button and put the two numbers up above each other. Um, so yeah, it's just I'm getting used to it now, but it's just I prefer the old one. I still we've got various calculators kicking about the house, but yeah, that this one is my least favorite. But I'm trying to stick to it because the other ones are being discontinued. So I feel it's probably wise to learn the new one so that when I get asked questions about it, I actually know how to answer them.
Yeah, I'm a bit done for if my calculator breaks before I have my exam.
They're pretty robust. I had the same calculator for like 20 years.
Oh, I've had mine's for like maybe 4 now, 3.
Yeah, I was when I was doing like A-level maths with Rebecca, I was still using the calculator I had at high school and used it right through university.
Oh,
Yeah,
good
it,
calculator.
it was a very good calculator. I loved that calculator. Then the screen started to go. The little LED screen went, so you couldn't read the numbers properly. So
That's so sad. One of the calculators at school, like I forgot my one when I was doing a test, and it was really weird because like on the screen how it normally just says the number.
Mhm.
This one would say the number and then put a decimal and fill the rest of the screen with zeros. But the decimal was really difficult to see, so I couldn't tell if it was telling me like 15 or 150.
Oh, yeah, I wouldn't like that.
Yeah.
Okay, let's finish up there, and I'll see you both on Monday for maths. Have a great weekend.
You too. See
Bye
you on
bye.
Monday.
See you
Bye.
Monday.